So welcome back. And the topic this week is very relevant for the final piece in project number 1. And this deals with resampling techniques. So I wanted to give you a kind of overview of why resampling techniques are important. So I'm going to reshuffle a little bit the order of the lectures, because last time I was thinking of talking about the statistical interpretation of ridge and lasso. But since I wanted to go through the resampling techniques, which is needed for the project, I would rather start with that piece first, because these are things which you will have to implement numerically when you analyze your data. So this is again a little bit about the statistics, which is needed in order to present the data and perform a data analysis with a statistical twist. So the lectures this week contain the statistical interpretation, in addition to the material we had for the weekly exercise, and then this material about resampling techniques. And there are two widely popular techniques. One which is called the bootstrap, which has been there since the 70s. And it was actually introduced by Efron, I think in 73 or 74, as a simple way to resample data. So your constraint is that in many, many cases, you don't have enough data. And then with not enough data, your statistical averages, because we are calculating like a mean average of the sample, you are calculating the mean squared error. And if you have some few hundred data points, it means that you may not have the ideal statistical expectation value for that specific quantity. And that's why people invented these resampling techniques. So you can run calculations which run for months, actually. So this is my case. And then you may produce a few hundred points. And then you would like to calculate statistical valid results. And you have techniques like the bootstrap, which was introduced by Efron in the 70s. This is actually a technique which first was introduced again as a kind of ad hoc technique. And then people have done the mathematics, and you can show that when you use this bootstrapping on identical and independent and identically distributed stochastic events, you should actually be able to reach the true value or the variance if you know the probability distribution. So the bootstrap technique is widely used in cases where you have some few thousand data points. Another technique which is widely used in machine learning is a technique called cross-validation. And we will discuss both of them today. And we will also bring in this discussion of this kind of holy grail in machine learning assessments of the methods which you're dealing with. And that is called the bias-variance tradeoff. And you will see that in basically any article and any textbook on machine learning methods. So these are the key elements. And then when we've done with that, we are going to look at the statistical interpretation of ridge and lasso. So hopefully, as you probably notice, I'm moving slowly. So let's see how far we get. There are also some nice movies. There's a link called StatQuest. I mean, it doesn't go so deeply into the mathematics, but these are nicely made movies between 6 and 10 minutes, which give you a kind of overarching view on the topic. The other thing is that I added at the end a note, the note which I sent in the beginning of the week about scaling. So this is now included in the lecture notes or the weekly slides this specific week. And there were some small missing things, and I just updated the codes. Yeah. 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 Okay. So I wanted to switch over to the whiteboard and just say a little bit about what we are going to see when we deal with project number 1. And that is going to give you a kind of overarching view of why we resample. So keep in mind that most of the cases you deal with when you have supervised learning examples, which is the case now, so this means labeled data, you don't have tons of data. So the typical databases are perhaps perhaps in the 100,000s, but not that more than that. So that means that when we calculate statistical averages, the statistical averages may not be equal to the true average if you knew this probability distribution, okay? So that's a kind of setting for what is coming now. So let's switch to the whiteboard and a quick look at the kind of overarching topic. So we are going to deal with resampling techniques. And these resampling techniques, the two very popular ones are called bootstrap. That means buksesele in Norwegian. And then we have the cross-validation. And cross-validation is the one which is widely used in machine learning applications. And this is a kind of what you might call a kitchen item, which you should have in basically all the projects you will be dealing with here. Okay? Now, what we have done till now is to define a function which we use to assess the quality of the model. So we have defined functions to assess the quality of the model. And the function which we have been using mostly is the mean squared error, and what we also have been calling for the R2 error. But you can also look at the absolute error, you can look at the relative error, or other measures which are relevant for you testing the quality of the model. To assess the model, and typically in our case, this is the mean squared error. And let's just call this a function of L. And then we could say that we have a data set, y of I, and then we have some y of I tilde, where this y of I tilde is the model which we are having. And then ideally, what we would like to have with a given training data, with given training data and test, given training data, which we call for T of I for this specific model. So I stands now for a specific data set. And this data set is now represented by a specific model. So I is not an individual data point, but this y tilde I is just a model. It could be a polynomial to a given order, okay? And this is trained with a training data, and then we apply this to a test data. This is the approach which we have been doing till now. And what we want then is to present some kind of error estimate for the test case, which is now a function which is given by this function which we have chosen for this specific data set and this specific model. So I stands for the specific model, and we have a training set and a test set. And we are applying the model to the untrained or unseen data tau of I. So this is the ideal. This is what we want to produce. And so when we have presented a model, then we always have to present to potential users of the model how confident we are about the quality of it. And then we have a measure like the mean squared error, which we typically would publish together with the model. Now, what happens is that we are going to run these kind of trainings many, many times. And if you looked into chapter 7 of the textbook of Hasty et al., there is a figure there, figure 7.1, where you see what can actually happen when you're running the calculations. So let's see what you're actually going to see in project number 1, and in all the projects you're going to deal with, and in all implementations of machine learning methods. So what you will be seeing now is something like this. Is that okay if I change page? okay? So in our case, what we will see is something which looks like this. Suppose now we have the predicted error on this axis. And then we have model complexity on this axis. And this is essentially what we will be doing in the project. And then you could say that if you look at the blue line here, this could be your training. But it doesn't need to look like that, because you could have run many experiments. Because typically what you would do now, if you take the training data, you would reshuffle the data so that next time you test your model, you just change the training data within the data set you have. So if you have 100 data points, you may pick randomly 80 points, and that performs one training model. The next time you pick randomly another 80 data points, if you have an 80%, 20% split, and then you repeat these experiments. So what you will see when you are running your calculations is that this may look something like this. So you will have a band of values. So this would be one training error. This could be another one. And if you do this many times, you would have a kind of belt here of values. Now, the thick line is then going to represent the average of all your trainings. So what you, yeah?
You are only training on that one data set.
The same data set, but you can pick the training set randomly. So that means that every time you train, you may not get exactly the same training error. Okay? So this is the resampling technique. And the reason why you do this is that this kind of approach allows you to treat the training in a statistical way. So you produce a lot of training data, and then you take the average of all the training errors. And if you're using techniques like bootstrap or this cross-validation, you can actually show that when you have enough data and you perform this enough times, you are approaching what might be the true value of the mean squared error. So what we are doing now, ideally, we would like to get the thick line immediately, but we won't get that. So what we can do then is to take the average of all the trainings we've done and then plot the thick line. So the thick line here is a result of the average of all the trainings we've done. So every training is then an experiment. You could think of this alternatively. Suppose you run an experiment every evening when you get back home, because you guys don't have any spare time problems, right? So you run some kind of experiment. Let's say you throw dice in the evening. And then you simply run the experiment that specific evening. So that would be one of these lines. And then you rerun it next evening. And then there may be different conditions because the temperature might be different. Or maybe you were just fed up with this course and you're angry when you get back home, and then the experiment turns out totally different. And then you would run this again and again and again. And at the end, you could provide an expectation value of all the experiments you've been running. This is typically what you would do. Now, in this particular case, you're rerunning the experiment again and again and again, and you're producing new numbers. Now, in our case, we cannot perform the experiment again and again because some of the experiments are extremely expensive and time-consuming. So what we are doing now is to reshuffle the data and treat every reshuffling as a new data set. And we train on that. So it sounds like cheating, but like for the bootstrap method, you can actually show that if these are independent and identically distributed events, you will actually be able to approach the true mean value and the true variance. Yep.
So I heard it does not mean a new data set, means reshuffling.
A new reshuffling of the same data. This is the basics of resampling techniques. Okay. So the next thing you would run then would be something like on the test data. And then ideally, you would like to see this. So this is your test data. But again, here, you may have a wide band from all the different experiments you've been running. So typically, the test data would be kept fixed, or when you do cross-validation, you would actually be changing the test data as well, as we will see. So the ideal now is that, or what you're going to calculate, so ideally you would like to have something which comes out immediately as the perfect error. But what we are going to do is to run a statistical analysis of this error. So what we will produce would be something which will be the average. So this error here, the true error which we will calculate, is then going to be, if we have n experiments, this would be the sum over all the experiments we are running. And then we have this function L of y of I, and then we have the specific model we produced with that specific training depth and test set. And then we calculate the average of all these mean squared errors. So every time you perform an experiment, you produce one mean squared error here, you produce another one here for that same model complexity, and then you simply collect all these and produce the error. So the reason why you do this is that these kind of resampling techniques allow you in a cheap way, without generating new data, to actually be able to give some kind of assessment of whether this mean squared error is a reliable quantity or not. So if you just run this once, you may get a mean squared error which may be too large or optimistically too small. But when you take the average here, you're actually performing a statistical analysis. And then you're providing an expected value for the mean squared error, or the error function which you have chosen. Okay? So this is a kind of overarching thing. So we will not go through all the details of these methods, but I wanted now to show you how you can actually perform this type of analysis with two very popular methods. One which is the bootstrap, and the other one which is cross-validation. And basically, all machine learning algorithms which are implemented, they perform this kind of cross-validation analysis. And these are the basic methods. They're extremely simple. They're simple to implement. And some of them also have a lot of deeper mathematics, which is quite interesting. So what I will be doing now is to switch a little bit back and forth between slides and the notebook. But before we do that, I wanted to derive these bias-variance equations, which is something which is used to actually analyze the quality of a model. And this bias-variance debate is something you will often see in connection with the mean squared error, because it's much simpler to interpret things in terms of the mean squared error. So you will often see the figures which like this one. What you will see is something like in the upper corner here, you may see something like a case with a low bias and high bias and low variance. And here we'll see something like a high variance and low bias. And often when people discuss the quality of a model and the complexity of the model, this is often done in terms of the bias-variance trade-off. However, in many cases, since it's sometimes is difficult to transfer this to other cases and regression cases, what people simply look at is this type of figure which you see here, without doing the bias-variance analysis. Okay? So for practical means, you could say now that when you hit that region where the red curve starts to increase, this is where you're trying to strike a balance between the complexity of the model and overfitting. So typically when it starts increasing, this is a signal of overfitting your data. And we will see this through many of the examples which we have in the slides here. But let's look at the derivation of this bias-variance trade-off and the way we would actually proceed by setting it up. So let's do that before we move on to discussing the different results and different programs and different implementation of Bootstrap and cross-validation. So the bias-variance trade-off, if we now look at the quantity which we are going to calculate, we will take the mean squared error, which is a very easy way by which we can illustrate this. So trade-off for mean squared error. So what we have defined then is that this mean squared error is typically given as the expectation value from I equals 0 to n minus 1, and then we have this y of I minus y of I tilde squared, where the tilde is our model. So when we look at these quantities, we are actually going to rewrite that in a slightly different way. And the way we will be rewriting this now is obviously in terms of the expectation values. So we will rewrite this as an expectation value of y minus y tilde squared. And when we are going to write this out, if we just do the plain rewriting of this one, so since we have the linearity of the mean squared of the expectation value, this means that we would have the expectation value of y squared. I get minus 2 times the expectation value. So I'm just writing out the terms. And y tilde, and then plus the expectation value of y tilde squared. So I'm simply using the linearity postulate about a expectation value, and then I just write it out. So what you will see now is that we're just going to manipulate this expression, and we are going to rewrite it in terms of the variance of the model, which we have, and something which we will define as a bias, plus the variance which comes from the stochastic noise. So if you look at the first term, or this term which is given by y tilde, we can rewrite that one in terms of the variance of y tilde plus the expectation value of y tilde. So this is just us using the definition of the variance. So this is this quantity squared. And this is also one of the things you are going to play around with in the project. And this is also partly one of the exercises in the project. And you will see this as a weekly exercise next week. So now we just rewrite that term. And when we now look at the next term, this y squared, we are actually going to rewrite that in terms of the approximations we have made, or the assumptions we have made, which is f plus epsilon. Epsilon is this stochastic noise, and this quantity is just squared, like that. And remember now that this f is a function which is now assumed to not depend on the probability distribution which governs y and eventually x. So when we calculate expectation values, we would say that this f is independent of y, in the sense that there is no probability. This f is seen as a non-stochastic function, as we have assumed. So f is a well-determined function here. So we can rewrite this one, and now if we just proceed, we would get an expectation value of this f squared, and that is just the value f squared itself. And then we have plus 2 of e of f of epsilon. And what we have next is the final term, which is plus E, the expectation value of this epsilon squared, which we have defined to be this variance. We assume that this epsilon follows a normal distribution with mean value 0 and variance sigma squared. So this term here is just sigma squared. This term here, since F and epsilon, they don't depend on each other, then we can separate it out, and we know that the mean value of epsilon is 0. So this term here becomes also 0. And then I'm just left with the first term and the second term. So if I now change page, this is something which we can rewrite as, let's just do that. So this would just be equal to F squared plus 2 times F times 0, which is the mean value of epsilon, plus sigma squared. Then the next term which we need to deal with is actually the term where we have a number 2 in front of it, but we have y times y tilde. And we would now introduce the model again, or the assumption we've made about the data. So this is F plus epsilon times y tilde. And then again, I use what's called the linearity of these expectation values. So that means that I can rewrite this as the expectation value of F times y tilde. And then I have plus the expectation value of epsilon times y tilde, like that. And this is something which I can rewrite, since y tilde and epsilon are also to assume to be independent of each other. So that means I can calculate the expectation values independently of each other. That means that I can rewrite this as the expectation value of F multiplied with the expectation value y tilde plus the expectation value of y. So y tilde and epsilon are independent of each other. So this is multiplied with the expectation value of epsilon, which is also equal to 0. So what happens then is that I can rewrite, when I collect all these terms, what I'm going to get then. So collecting all these terms, what we have now is something which runs like F squared minus 2 times F multiplied with the expectation value of the model which we have made, plus this sigma squared, plus the variance of the model. So this is the deviation within the model itself, plus this quantity which I simply call y tilde, and this quantity is just the mean value, but it is squared. So if you now look at what we have the variance of the model itself, and now I'm going to plug in this quantity here, and I'm going to define a new object. And we also have the variance of the noise, which we have added. So if I collect everything, I can rewrite this in terms of the following expectation values. So this becomes equal, when I collect everything, it becomes equal to the expectation value of this F minus the expectation value of the model here. So this is y tilde squared, plus this sigma squared, which we don't have any idea what it might be. So this is very dependent on the noise. And plus the variance of the model itself. So this means how much your predictions vary internally. Okay? Now, these things have different names. And you will see now immediately why this is called the bias. This is called the variance. And when you do a fitting of a specific method, you're going to deal with something which is called the bias-variance trade-off. And I will try to explain to you what that means in terms of a simple cartoon. But this is a kind of analysis you end up doing when you're looking at the complexity of your model and how that fits the data you have. So the other sigma squared is a quantity which we don't know. Now, for all practical means, because at the end, we don't know f. This is an unknown quantity. So we need to plug in something if we want to calculate, okay? So that means that the bias, when we want to calculate the bias, is now going to be approximated with 1 over n, the number of data points which we have. And then I have I, 0 up to n minus 1. And now we, instead of having f of I, we take the data because we know the data. So we are making an approximation here because we don't know f. And you would dearly like to calculate something. So, and then we have minus, and that's the expectation value of your model squared. The variance is something you can calculate immediately. That is going to be given by, again, the number of points you have, and then it's y of I tilde minus the same expectation value. So when you're doing this bias variance trade-off, these are the quantities which we're going to evaluate. And that's going to tell us a little bit about the complexity of the model. It's something which is easy to run when you look at the mean squared error and the typical analysis which you will see in essentially all textbooks and all examples deal with the mean squared error and you fitting a continuous function. It's much more difficult to extract a similar, how to say, easy division between this bias and variance. So what does this mean? So let's try to gain some kind of intuition about what these expressions can mean. And let's just look at an example, which you will also find in many, many textbooks. Suppose your target is here, and then you have circles. So you could think of you guys, when you're getting close to the end of the semester, you're just fed up of me, and I'm the target here, and you're throwing things at me. And then you can see how close you get and how far you get. And that depends on how far we are in the semester and how good your aim is. But let's now think of a case where we have a high bias. So this is the ideal, right? This is what you want. So a high bias means that your data points may be here. So you're far away from the ideal. So your data points of the model, they are now, so let's use a different color here. So this is what you're getting. So suppose your data points are here. Something like that. So this will mean that you have a high bias because if you take the mean value of your data points, they are far away from the ideal value. So you have a bias in your data, in your model. Does that sound reasonable? So this is typically what you mean by a high bias. Now, what you should also see here, if you now think of the model, so this is what the model is producing. So these are the model data. And this has the mean value. So the mean value could be a point here. And you see you're far away from the ideal. So this is the mean of the model. Now, if you look at this spread in model predictions, what would you say about the variance of the model? Is it small? Is it large? Yeah? Yeah, it could, maybe I should exaggerate it a little bit. Let me exaggerate it. Like that. Would you agree that we could say we have a big variance? So we have a big spread in the model predictions. So the model has points far away from the mean value. So we have a high bias and a high variance. So here we would say that we also have a high variance. So that would be one specific case. Now let's now move to another case, and let's look at same data. And we have the circles here. So that was something you tried the first time when you were fed up with me. Then the next time your aim is getting a little bit better, and then you're getting closer, but then your mean value is still here. So let's just, this is a model which you have, but now you have something like this. So these are the different points, and this point is actually the mean value of your model. So if you look at this one, what would you say intuitively is the variance in your model? Would you say high, low? This would be a low, but you would still have a high bias because you're far away from the point you want to reproduce, right? So you would then have a high bias, and you would have a low variance. So a high bias, if you now think of the model you're making, if you have a high bias, what kind of model complexity would you expect from a high bias? Would it be complicated, or can it be just a cheap model? Yeah. If I want the true value, so suppose I have a high bias, what would you expect if you now go back? Suppose you go back to this figure which we plotted in the beginning here, and you're looking at your test error. So what would you think of would be possible here? High bias or low bias? Model complexity, how do they relate? Yeah.
The model prediction quite far away from the true value needs to be quite complex.
It does not need it. It could also be that you are in the other case where you have a high bias because you are missing completely. You have a too simple model. So if I'm fitting a sixth order polynomial with a first order polynomial, most likely then the bias will be high. Does that sound reasonable? So we have two more cases. So this will be high bias, high variance. Here we have low variance and high bias. But we could now have a case where we have something like this. And now I'm getting what I will call, so now I have to remind, high bias, low variance. So we could have a low bias, and so we had a low bias, no, low bias. So suppose now the mean value is here. This is the mean value of the model. So we're getting pretty close to the ideal result. But then these are the individual predictions which the model is making. So this will be a case of low bias. But we would have a high variance. So this is a high variance. And what you will see then, when you go back to this model figure here, if you look back at this one, is that you will often, it's not every case, but you will often see a case like this one. So this will be a flag for overfitting. You will have a low bias because you're getting pretty close to the mean value, but you have a big scatter in your model. So typically, this is what you will see when you have a high bias and a low variance, and a low bias and a high variance. And then the final case, which is actually the holy grail, what we want to have, and you can guess what that is. That would be an almost perfect fit. So we would have the ideal point here, and then we have these different circles again and again. And then we would have the mean value of the model here. And then we have a case like this one, where all the values are centered around the mean value. So this would be a case of low bias and low variance. So these are the 4 cases which we can analyze with this type of bias-variance trade-off. And the whole thing deals with how much you deviate from the ideal value. So what we're going to do next now is to study this and see if we can see something like what we see in textbooks. And if you go into this textbook by Hasty et al., like this figure 7.1, this is a typical figure you will see again and again. So I'm going to show you an implementation of the bootstrap algorithm. So the bootstrap algorithm is extremely simple. It's called resampling with replacement. So that means that when you generate the next data set, you can actually pick the same data point several times. This algorithm is extremely simple to implement. And we are going to analyze the bias-variance trade-off for the function you've seen in the exercises right after the break. But we need just to say what the bootstrap method is. And so let's quickly mention the bootstrap method before we take a break. And then you have coffee in the break, guys. So the bootstrap method is actually pretty simple to implement. So suppose you have an original data set. So we have a data set. So we have a domain of points, and I'm just gonna simplify this to some Z1, Z2, up to some Zn. And we assume that these guys are all independent and identically distributed. Actually, the bootstrap works normally best for that kind of data points. And the example which I have in the Jupyter notebook is an example with a Gaussian distribution. So this is a cheap way to just perform a sampling again and again using the same data. So the first thing you do now is the bootstrap sampling. You draw a bootstrap sample. It's normally called a bootstrap sample. And we're just going to call this D1 with a star here because it's going to be different from the previous one. And we have a Z1, a Z2, up to a Zn. And note now that this is done with replacement. This means that if Z1 originally was number 2, when I do replacement, I bring it back again. And next time, when I pick randomly a number, I can pick the same number again. So I could have Z1, 2, Z2 equal to 2, and so on. So the idea is that you're going to make chains of numbers which are supposedly different. You pick randomly, but you also have replacement, which means that you can have the same number again. Yeah. The number of data is the same. Yeah. So it's and in Python, this is a function which is called randint something, which just reshuffles the data for you with replacement. So it's very simple to implement. Now, what you would do then is that you would compute some expectation value. So suppose now that you compute the mean squared error, and I'm going to compute theta 1 with an asterisk, and this is some kind of expectation value, could be the mean value. Just to give you an example, suppose it's the mean value. And then we just repeat this many times. So the next step, repeat many times, or repeat B times. And then you get the estimates. So these are the estimates of the parameters you're interested in, getting estimates. It could be the mean value, it could be the variance, it could be the mean squared value, etc., etc. You decide what kind of expectation value you want to look at. And then you would get a series of theta 1, you have a theta 2, and all the way up to the final. So every one of these can be thought of as an experiment. And then the final value, which I'm going to call like this. So these are quantities like that. And then I have a 1 over B. And then I sum over all the experiments I've been running. And then I have this theta J up here. And when I'm done, I could, for instance, if this is the mean value, suppose this theta is the mean value, then you can compute the variance with that quantity. And you could compute the variance of sigma of theta, which is simply 1 over B. And then you have a J equal to 1 up to B. And then you have this theta J minus this theta, the average value squared. Or you can compute other quantities like the mean squared error. Now, the example I will show after the break, I'm just stealing 3 minutes of your life here. And hopefully I can give them back sometime. But the quantities we are going to look at after the break, we are going to use a normal distribution or Gaussian. And there the central limit theorem kicks in, and we know what we should get for the variance. And you will see that from this numerical demonstration that the bootstrap method is giving us what we expect from the central limit theorem. So if you have independent and identically distributed events, you will often get, or you will normally see that the bootstrap gives you what you expect, which is pretty good. So the bootstrap is often used as a resampling technique. Then after the break, we will also look at cross-validation, which is normally used in all machine learning applications. And it has to do with the fact that cross-validation is cheaper computationally than bootstrapping. I hope you see the overarching view with the bias-variance trade-off. This is a way to analyze the complexity of the model. Any questions? So we have coffee in the break. So let's do 15 minutes and be back at 1:20, if that's okay.